Alright, so in this video we will do another problem. We will try to answer that, and the problem would pertain to instantaneous velocity, average velocity, and the concept of average speed. These are three different things that we have studied so far, and it will be nice to see them used and employed in a problem. So this is the question 3 for the video series of scalars and vectors. So let's get rid of this for the moment, and this as well. Alright, so what's the problem? Well, the problem is that, or the question that I want to pose, is that the body moves with the position vector at different points in the trajectory given by the vector r as a function of t as 10 cosine pi by 2 times t I cap plus 10 sine pi by 2 times t j cap. So there you have it, that's the position vector of a particle at different times t. Now you notice the only variable you have in this equation, or expression rather, is the variable of t, and t is the time. So if you input different values of t, you get different position vectors, and if you connect all of them up, you get the entire trajectory of the body from the low minimum of the time to the upper maximum of the time. That is to say, from when you start measuring the body's motion to when you stop measuring it. So here we consider the motion of the body from time belonging to 0 to, well, 2 seconds. So like so. That is to say that we want to consider the motion of the body at time equal to 0 seconds, and we will continue to observe the motion till time equal to 2 seconds. So let's draw how the position vectors actually look like. And for those who don't know, this is pi, and the angle here is measured in radians, and this is the cosine function, this is the sine function, and I and j are the position vectors in the x and the y, are the direction vectors in the x and the y directions. They're unit vectors in either direction. So let us plot the position vectors at different times. So there we have our x-axis, there we have our y-axis. Oh, I'm so sorry, this is the x and this is the y. What's wrong with me? So there you have your x and y. It's obvious now that the I cap vector is going to point in the x direction, positive x direction, and the y cap vector is going to point, or the j cap vector is going to point in the vertical direction along positive y direction. So with those things in mind, we can now plot what r of t looks like at different times. So let's start from the lower minimum, or time t equal to 0. So r of 0, or 0 seconds, if seconds is the unit we want to measure the position vector in, would be equal to 10 times cosine, 0 I cap plus 10 times sine 0 of j cap. So this gives us, 10 I cap, because cosine 0 is 1 and sine 0 is 0. So you only get the contribution from the I vector term. So that's here. So if we were to plot this now, r at 0 time, the body would be at 10 I cap. So if this distance is 10 units, then the position vector of the body would be this, originating from the origin at O, ending at this point there. Say this point is at 10 units from the origin. So that's, let me write it here. This is r of 0 at 0 time. We do the same thing at r of 1, that's at 1 second, and we get 10 times cosine pi by 2 times 1 is pi by 2, I cap, plus 10 times sine of pi by 2, j cap. We look into the tables of sine and cosine functions, and we get to know that the value of cosine pi by 2 is 0 in this case, so it's opposite from what we had in the previous case, and sine pi by 2 is 1. Therefore, you only get the contribution from the second term, and that is 10 j cap. So now, after 1 second, the body, which was initially here, the particle which was initially here, suddenly comes down to this point, which is located, once again, 10 units from the origin, but now in the y direction. So this is 10 j cap vector, or this is r of 1 second. We do the same thing yet again, and we realize that r of 2 is, well, 10 cosine of pi by 2 times 2 is pi, I cap, plus 10 times sine pi by 2 times 2, which is pi, j cap. Now, if you solve this up, sine of pi becomes 0, but cosine of pi becomes negative 1. So your answer becomes negative 10 times I cap. So the body now from here goes to here, which is at 10 units from the origin, but in the negative x direction, and hence the vector negative 10 I cap. So there you have it, 10 I cap in the positive direction is your initial point at time equal to 0 seconds. Then at time equal to 1 second, the position was here at the position vector of 10 j cap. And finally, at time t equal to 2 seconds, the body was at here, 10 units from the x direction, but in negative, giving the position vector to be negative 10 I cap. So this is how the body is moving, and it takes a certain bit more mathematical analysis to realize if this is your x coordinate and this is your y coordinate, then the locus of the body comes out to be x squared plus y squared equal to 10. So that is to say, if you call this x, if you call this term y, and you eliminate t, and one very nice way is to square both the terms and add them up, you get a constant, and that is 10. So x squared plus y squared equal to 10 is basically, is 100, I'm so sorry, is basically a circle of radius 10. So the circle would look something like this. So the body starts at this position here, goes in this direction, keeps going in a circular manner, ends up at this vertex, then goes on, continues its motion, and at time t equal to 0, stops right there, or basically ends up being right there. I don't know if it stops or not, but it certainly ends up being right there. So this is how the body is moving, and this is a circle. Circle of radius 10. So the trajectory of the particle has been known just by looking at the position vector. So what can we do with this information? Well, there are many things we can do with this information, and certainly there's 3 things that we wanted to figure out in the beginning of this video is something that we can evaluate now. Those 3 quantities are average speed, average velocity, and instantaneous velocities. So let's tackle average velocity at first. So let's get rid of this as well, this as well. Let me get rid of this for now as well, and redraw it again. So for better representation, let us have our x and y. Let us draw it like this. So this is our y-axis, this our x-axis, and our body now moves in a circular manner. So let me do my best to draw a circular trajectory. Okay, wait, that will work. This seems more like it. There you have it. That's the trajectory of the particle, but let's get rid of the lower terms, the lower part of the circle. So that's, okay, that's this part. Alright, so this is your trajectory of the particle. It starts from this position here, goes like this, ends up being at this point, it goes like this, and ends up being at this point at time t equal to 2. So this is at t equal to 0, t equal to 2, this is at t equal to 1. So you have 3 positions that we have evaluated the position vector at, and there you have it, that's the motion of the particle. Now what we can do is let's tackle average velocity. Alright, so what do we know about average velocity? Well, average velocity, to measure average velocity, we need to consider the time interval over which we are evaluating this quantity of average velocity, and we need to know the displacement between those 2 times in terms of positions. So let's consider the average velocity between t equal to 0 second and t equal to 2 seconds. So at t equal to 0, well, r of 0 was 10 I cap, the body was here at 10 I cap, position vector from the origin, this being the position vector, and as we went further on at r equal to 2, the body was at minus 10 I cap. So the body was there. And the position vector corresponding to that was this. So in order to calculate the average velocity between these two time intervals, what we need to do is we need to evaluate the difference. So I would write average velocity would be the displacement vector divided by the time. The displacement vector is r of 2 minus r of 0. If you subtract r of 2 from r of 0 from r of 2, you get the displacement. And the displacement vector starts from the initial position, which is here, and should go all the way till the final position. So this is the displacement vector we are looking for. Let's see if that comes out to be the case. So r of 2 minus r of 0 comes out to be, well, r of 2 is negative 10 I cap, r of 0 is 10 I cap, so that's negative 10 I cap. What you get is negative 20 I cap, which is the case because 20 is the diameter of the circle, and it's in the negative direction because this displacement vector, d vector, points in the negative I cap direction. Positive I cap is in this direction. So this makes sense, and this is indeed the numerator. What with the time? Well, the time would be the difference in time at which we are considering the motion. So that's at 0 and 2. The difference between 2 seconds and 0 seconds is, well, 2 minus 0, or 2. Therefore, the average velocity between those two time intervals comes out to be negative 20 I cap from the numerator, that's what we evaluated there, divided by 2. Hence, it comes out to be negative 10 I cap. This is the average velocity. So the average velocity has been halved in its length from the displacement, which should be the case because time is 2. So let me just write it down here. The average velocity came out to be negative 10 I cap. So it seems as though the body is going in the negative direction, even though average velocity corresponds with sort of an average measure of the speed. It does make sense in some way. If you look at the motion of the body, very crudely it seems as though the body is going in the negative direction, and hence the negative sign. But in reality, the body takes a much more complex way of motion. In fact, it goes around a circumference of a circle of radius 10. And that is something that's not included in the average velocity term that we evaluated. Well, so far so good. Average velocity is something hypothetical, but it does help us to understand the motion, even though in a very crude manner. Now let's go to something more, I would say absurd, but something rather more important. We're talking now about the average, or let's change the pen now. We're talking about average speed. So average speed is a scalar. It's not a vector. Average velocity came out to be a vector, hence you have the I cap sign there, so I cap right there. Average speed has to be a scalar and must not include anything to do with the position vectors I or j. It simply should be a magnitude. From the definitions, we know that the average speed turns out to be the distance divided by the time. Again, we need to consider average speed between two instances of time. We do the same as we did with average velocity. We would consider the motion of the body from t equal to 0 to t equal to 2 seconds. Therefore, our time interval between those is 2 seconds, and the distance would be the distance traveled by the body between those two time intervals. Therefore, the distance would be this length of this circumference of the semicircle. So the circumference or the perimeter of this semicircle would be the distance, or the length of the arc, and that would be 2 times pi times the radius divided by 2, because we're only considering half of the circumference of the entire circle. That gives you pi times the radius, and radius from what we already know would be 10, because of this term here. That would be 10. So the distance is 10 times pi, or pi times 10, and the time is 2. That gives the average speed to be, well, 10 times pi divided by 2, or something like 5 pi. So this is the magnitude of average speed. Let's write it here as well. Average speed is 5 times pi. Now, if you look at the magnitude difference between average velocity and average speed comes to something around 15. If I'm not mistaken, let's evaluate 5 times pi. That comes out to be 15.7. So this is 15.7. However, the average velocity magnitude comes out to be only 10. And the way I can say that is if I look at the magnitude of average velocity. I is just a direction and thus does not contribute anything to the magnitude. The only magnitude contribution comes from this term here, which is 10. So average speed is a greater term in terms of magnitude than average velocity. It can happen, that happens because distance is usually more than displacement. Because distance traveled between time equal to 0 and time equal to 2 is this length of the arc. However, displacement was this straight line. And if you notice in Euclidean geometry, a straight line is the shortest distance between 2 points. So displacement is almost all the times smaller or equal to than distances. And if you divide this expression by time, you get another expression in terms of, velocities, because displacement by time is average velocity is less than or equal to average speed, which comes from distance by time, not displacement by time. So this is valid here because average speed is somewhere around 15.7 approximately, but average velocity is somewhere around 10, only in terms of magnitude, and that is why this expression holds. So there you have it. That's the average velocity and average speed. But there is something more critical to evaluate now, because so far we have evaluated terms like average velocity and average speed, which really don't make much sense in terms of what's actually happening to the body. One considers a direct movement from the initial position to the final position, and hence completely disregards what's happening to the body in between, for it takes a circular path, not a straight one. The other does take the time, the distance into considerations, but gives you a rather abstract value, because the velocity direction keeps on changing all the while throughout its motion, but does not hold a constant value like 15.7. And I'm talking about average speed here. We know that the body moves in a circular path, and so its velocity at each instant changes. For example, initially we can only expect its velocity to be in the y direction, and at some later point, at this point, the velocity vector must be tangential again and should point somewhere like this. At the top, that is at t equal to 1 second, the body would be in horizontal motion and should be pointing in the negative x direction in terms of its velocity. So on and so forth, we would get a velocity like this, velocity vector like this, and finally the velocity vector must point downwards. So the velocity is changing. Even if it's remaining constant in terms of magnitudes, that's something that we can expect it to do. Its direction keeps on changing, and that is not encountered and not taken into account in either of these quantities of average velocity and average speed. So to account for that, we describe something which is known as instantaneous velocity, or the derivative of the position vector, and that is something we want to evaluate now. So let's get rid of this and look at the way to evaluate, average velocity, instantaneous velocity. So instantaneous velocity. There you have it. So instantaneous velocity is given as a function of time at that instant, and it's represented as r of t plus dt minus r of t, where dt is really small, divided by dt, in the limit that dt goes to 0. So this is to say that dt is very small. If you evaluate this, this comes out nothing but the derivative of the position vector. So in order to evaluate velocity at that time and at the time instance, we need to evaluate the derivative of position vector at that time instant. So let us consider a more general case. We evaluate velocity at a general time t. So v of t would be d by dt of the position vector at time t, and that is given by this expression right there. So let's write that expression down. That is 10 cosine pi by 2 times t I cap plus 10 times sine of pi by 2 times t j cap. That is the position vector. We take the derivative of this expression, and that gives you 10 from the first term, and when we take the derivative of cosine times something times t, the coefficient of t comes out as pi by 2. Cosine's derivative changes to negative sine, so that's negative sine pi by 2t. I cap remains I cap. That is the derivative of the first term. We do the same thing for the second term. 10 from here, pi by 2 comes out from there. Sine's derivative is cosine, and you have the term pi by 2 times t inside, and you multiply that by j cap, because the position vector does not change. So the velocity, instantaneous velocity vector, also looks very much like the position vector, and sort of takes the same form. If you write this in a more compact fashion, it comes out to be 10 pi by 2 minus sine pi by 2 times t I cap plus cosine pi by 2 times t j cap. So there you have it. That's the position vector of that's the velocity, instantaneous velocity of the body at time t. But what does this really mean? Well, it gives us a vector very much like the position vector that we had initially, which kept on changing at different times. For at time t equal to 0, the position vector was here. When we moved on, the position vector was there. Time t equal to 1, the position vector was vertical, so on and so forth, until at time t equal to 2, the position vector was there. So it gave a position vector which kept on changing. What about this? Well, this also gives you a position vector that keeps on changing, and the way we know that it's changing is because it's a function of time. You see the t's right there, and that indicates that this is a function of time. But what does this really mean? Well, to evaluate that, the best way to look at that is to evaluate the velocity vector or the instantaneous velocity vectors on different times. So let's hope they match with these orange vectors we anticipated previously. At time t equal to 0, the velocity vector becomes, well, 10 pi by 2 as a constant outside. Sine of 0 comes out to be 0, so that's 0 I cap. But cosine of 0 comes out to be 1, that's 1 j cap. So the velocity vector at time t equal to 0 points in the vertical direction because I component is 0. That is 10 pi by 2 j cap. So it is indeed pointing in the vertical direction, in the positive vertical direction, in the positive y direction. And that is the case here. So this matches with what we anticipated. What about velocity at 1 second? Well, at 1 second the body is here, and the velocity of the body should be in the negative x direction. Let's see if that's the case. And to evaluate that, we simply put t equal to 1 in this expression. 10 pi by 2 is a constant that comes out. Sine of pi by 2. Well, sine of pi by 2 is minus 1. Well, because of the minus there. Sine of pi by 2 is 1, and minus of that is minus 1. So you have minus 1 I cap. What about cosine of pi by 2? Cosine of pi by 2 is 0. So you have 0 j cap. Therefore, at t equal to 1 second, v of 1 comes out to be negative 10 by 2 pi I cap. So it is indeed pointing in the x direction and even in the negative x direction, which is the case as what we anticipated at this point. So even that has been taken care of. What about at time t equal to 2? Well, v of 2 seconds comes out to be 10 pi by 2 as a constant. Now you put t equal to 2 in this expression, you get sine of pi by 2 times 2, which is sine of pi. Sine of pi is 0. So that's 0 I cap, regardless of the sign there, plus cosine of pi. Pi by 2 times 2 is pi. So cosine of pi comes out to be, well, negative 1. And that is in the j direction. So at 2 seconds, or at time t equal to 2 seconds, the velocity points in negative y direction because of the negative 10 pi by 2 j cap sign. So which is also indeed taken care of from our diagram. So even that happens. If you were to do something more involved, you could also evaluate the position, the velocity vectors as well as the position vectors at time t equal to 0.5 seconds, and you would notice that it points in an abstract direction of this vector. If you do the same thing at time t equal to 1.5 seconds, it would be pointing in this manner, such that this angle here is 45 and this angle here is also 45 as well. So there you have it. That's the instantaneous velocity. That was instantaneous speed of 5 pi, and that was the average speed, and that was the average velocity of minus 10 I cap. So out of all the three quantities that we evaluated so far, we realized that instantaneous velocity closely matches to what's actually happening to the body. It keeps on changing with different time. It's not a constant irrespective of the time, which is not the case with average velocity and average speed. So that is to say that instantaneous velocity carries more information than average velocity and average speed, and hence is more useful than these two terms right there. But these two terms form the basis of how we define instantaneous velocity. So in totality, all the three of the terms that we ended up evaluating are important. It's just that instantaneous velocity is more handy. So there you have it. That was a question where we were asked to evaluate average speed, velocity, and instantaneous velocities, and we ended up doing that by taking the derivative of the position vector for instantaneous velocities and subtracting appropriate distances and displacements and dividing it by time in case of average velocity and average speed. And we got a vector, a scalar, and vector again in case of instantaneous velocity. So I hope this video made sense. I hope it helped you understand the importance of the three quantities we ended up evaluating, and I hope it gave you insight in terms of dealing with questions like this, where you were given a position vector and you're asked to evaluate many terms and many quantities related to that. So all the best and have fun.